Assalamualaikum. So today we would like to present our task 1, the growth population in Indonesia from 1999 to 2023, and our task 2, Newton-Raphson rules. So this is our team members, which is Alia Nuraisha, Radin Damia, Tisha Alisha, Ainin Hassana, and also Fatma Azhar.
This task is to be carried out to fulfill the objectives of the assignment, which are as listed below. In the task, we mainly focus on the application of the first-order differential equation to the total population in Indonesia from 1999 to 2023. At the end of 2023, the population in Indonesia was 281,100,067. In 1798, Thomas Malthus, an English clergyman, scholar, and economist, developed a fundamental concept for modeling, and the implementation of the Malthusian model used in task 1 is to find the growth of the population in Indonesia. The Malthusian model assumes that the rate at which total population in Indonesia increases at a given time is proportional to the number of populations at that time. The Malthusian model can be written as Tp over dt equals to Kp, where Pt is the number of populations in Indonesia at time t years, and K is a constant of proportionality.
In this task, we apply the Malthusian population model, which is based on the first-order differential equation. Pt represents the population at time, K is a constant representing the rate of growth. We start by separating the variable in the equation. This allows us to isolate the variable so we can integrate each side independently. We now integrate both sides, which gives us ln P equals to Kt plus C, where C is the constant of integration. Next, we solve for Pt by exponentiating both sides. Then, we substitute the t equals to 0 for the 1999 population value as the Pt. Then, from the equation we have obtained, we replace the t equals to 1 and the population value of 2000 to the equation to find the k value. So, the equation of the particular solution was obtained.
Table 1 presents data on the actual population of Indonesia from the year 1999 to 2023. It shows a consistent yearly increase in the population over the 24-year period. In 1999, the population of Indonesia was recorded at approximately 213 million people. This number steadily rose each year, reaching around 281 million by 2023. The data reflects a total population growth of over 68 million people during this time span. This table 2 compares actual population figures with values derived from a mathematical model. The columns include the year, the time variable t representing the number of years since 1999, the actual recorded population for each year, and the particular solution, which represent the population estimate using the Malthusian model. In this context, the year 1999 is used as the base year, which is t equals to 0. The particular solutions values were calculated using the formula we obtained to estimate how Indonesia's population would grow over time. The graph illustrates the comparison between a particular solution derived from a Malthusian model and the actual population data over a span of 25 years. The vertical axis represents the number of population in scientific notation, while the horizontal axis shows time in years. The yellow line marked with crosses indicates the particular solution, which is a theoretical prediction based on an exponential model. In contrast, the blue line with diamond markers represents the actual recorded population data. Initially, both lines are closely aligned, suggesting that the model accurately reflects real-world growth in the early years. However, as time progresses, the yellow line begins to diverge and overestimate the population compared to the actual data. This growing gap highlights how mathematical models, while useful for prediction, may not fully account for real-world constraints such as limited resources, policy changes, or social factors. The graph ultimately emphasized the importance of validating theoretical models against the actual data to ensure accuracy and relevance in long-term projections.
Now I'll be presenting the future and past value of population from the particular solutions. To determine the number of human population in Indonesia in the future from t equals to 0, we have taken few numbers, which is t equals to 10, that gives the population value 243,835,033. Secondly, we also took t equals to 30, which gives the population value
329,274,551.
Other than that, we also determined the number of human populations in Indonesia in year past from t equals to 0. Few numbers were taken, which is t equals to -5. That gives the value 198,647,825. Other than that, we also taken t equals to -15, and the population value was 167,501,432. Based on the calculation, the population values predicted by the Malthusian model are not exactly the same as the population of Indonesia from 1999 to 2023. The graph shows that the predicted population keeps increasing fast every year, but the real population grows a bit slower. This difference becomes more obvious after 2010. For example, in 2023, the actual population was 281,190,067, but the model predicted 300,898,170. The average percentage error between the actual and predicted value is around 1.491%. This shows that the model is quite close, but not completely correct. The curve from the model is steeper than the actual population line, which means the model starts to overestimate the population as the year goes by. This happens because the multi-scene model assumes that the population will always grow continuously and exponentially. However, in real life, many other factors affect population growth, like birth rates, death rates, government rules, people moving from one place to another, and economic situations.
Indonesian population growth has been shaped by several key factors. Number one, family planning. Program the Keluarga Berencana program started in the 1970s promoted smaller families with the slogan Dua Anak Cukup. It provided access to contraceptive and reproductive education, reducing fertility rates significantly. Number two, healthcare improvement. Improvement in vaccination, maternal care, and nutrition lower infant mortality rates, reducing the need for larger families. And number three, urbanization and economic development. Urban growth in cities like Jakarta, Surabaya lead to the lifestyle shifts such as delayed marriage and career focus, resulting in smaller families, especially in the middle class. Next, we move on to the factors that can impact future population. Number one is Asian. By 2045, 70 to 80% of Indonesians are expected to live in the city. This shift may lead to smaller families, rising housing costs, and also food rationing and infrastructure strain. Cities like Jakarta already face overpopulation and congestion. And number two is migration patterns. International migration for work and study is increasing. Meanwhile, internal migration to cities may leave rural areas with aging population and also labor shortage. We move on to the conclusion. Based on the analysis in task 1, we recommended that using monthly data instead of yearly data for future studies on population growth in Indonesia. Yearly data contains larger intervals which may overlook subtle yet important changes. In contrast, monthly data allow for more detailed tracking for enhances the accuracy of predictive model. We also encourage researchers to continue studying Indonesians' population growth regularly. Frequent updates will help improve the precision of model like motorization model, making prediction more reliable. This will support better planning for essential sectors such as healthcare, education, and urban development by aligning policy decisions with the real-time population trends.
For task 2, this is the task given for our group. And to apply the Newton-Raphson formula, which is xn plus 1 equals to xn minus fx over f prime x, I did the derivative of the formula given, and this is what we got. Next, in Excel, for task 2, we have 4 columns, which is x, fx, f prime, and x minus f over f prime x to find the next x value. So here are the equations, and I've turned it into Excel format so I can just easily copy paste it here. So first, we sub in the first x value, which is 0.5. Next, what I did is copy the equation from B1 and paste it on B2. Then I replace the x by clicking A2 to replace x with 0.5. Then I did the same thing for f prime, copy the equation from C1 and paste on C2, then replace x by clicking A2, then we'll get the value. And lastly, to find the next x value, I'll just click A2 for the x minus B2 fx over C2 for the f prime x, then we'll get the next x value. Next step is I'll click on D2 to represent the second x value to put it on A3 and drag each column, then Excel will calculate it, the fx, f prime x, and the next x value using the same formula I did for x equals to 0.5. At the end, the value of x will converge and the fx become very close to 0. Final x value is 0.845222, and these are the roots for the function.
Next, let's look at the graph of the Newton-Raphson method based on the function we use, which is fx equals to e to the power of x to the power of 3 plus ln 2 to the power of 2 plus 2x minus 2. This part helps us visualize how the values of x are getting closer to the root through each iteration. As shown in the graph, this is the curve of our function. The Newton-Raphson method is used to find the root, or in other words, the value of x, where fx equals to 0. So we started with our initial guess, which is x1 equals to 0.5. Then we apply the Newton-Raphson formula step by step. Xn plus 1 equals to xn minus f xn over f prime xn. From the calculations shown earlier, we can see that the values of x start to converge. After several iterations, the results stabilize around 0.845222, meaning that is the estimated root of the function. From the graph, we can see that the curve is increasing smoothly. This shows that our function is suitable for the Newton-Raphson method, and our chosen starting point is close enough to the actual root. So, through this graph and calculation, we can conclude that the Newton-Raphson method is effective in finding the root quickly as long as the function is continuous and the initial value is chosen wisely. That's all for the explanations of the graph.